Hey, what's up? Welcome back. In this episode, you'll learn how to solve part 1 of day 16 for the advent of code. This one is about all of these valves and tunnels and flows, and we're going to go through some tunnels to turn on some valves, and we want to see if we can optimize our traversal through this graph so that we have the highest flow rate at the end. And so the puzzle, the way that the puzzle is presented is that you have 30 minutes before the volcano that you're inside of is going to explode. And we don't have time to get out. And so what we need to do is go around and change or open all of these different valves. So the valves are going to start off as closed. And this is the input we receive is we're going to get the name of a valve, its flow rate, and then some tunnels from that valve that lead to other valves. And we want to figure out the best way to go through each of these different tunnels in order to turn on all of the valves. And once a valve is open, it will release some pressure, and the pressure is the flow rate times however many minutes that it's open. And so again, because we only have 30 minutes, it's constrained to that 30-minute window. We need to figure out some algorithm to traverse this graph. And in fact, the first thing we want to do is actually just build a graph out of this. So I'm going to start off with dropping our input here at the bottom, and if argv is empty, we're just running this sort of as the examples or this test mode. We want to say data is data.readlines. Otherwise, we'll say data is file.readlines. And in both cases, we will chomp to make sure that we don't have that new line at the end, and we should be good. All right, so the next part is that we want to parse out all of our valves into some graph or some map of the tunnels. But we'll just say that our valves is going to be some dictionary, and we'll use a constant so we can write a couple different methods and still have access to it. And we also want to have a graph. So we're going to have two dictionaries here. One is going to hold the valve and its flow rate. It'll just be a mapping of A to 0, BB to 13, CC to 2. And then we're also going to keep a graph, which is going to be AA to its adjacent valves. All of the different valves that are near, we'll go through data. We'll say data.each line, and we want to map the line so that we can pull out the details here. We're just going to we'll use regular expressions again to figure out what we want. Now, there's one interesting thing about the regular expression for this use case, and that is that for some of these, we have plural and some we don't. So we're going to use rubular again today. And what we want to do is say we grabbed one of these inputs, and that's matching perfectly. We want to grab off the name of the valve. I'm going to use a capture group here. We'll say that this is the name, and it's actually like just A to Z, and there has to be two of them. So that gives us one capture group for A. Then we want to, okay, so now it says has the flow rate. We want to grab the flow rate. We're going to say rate, and this is going to be an integer. There is no negative rates. And then here at the end, we have tunnels lead to valves, and then some list of valves at the end. So let's just replace all of those with something else called, I don't know, valves. And this is going to be, I don't know, some words. And actually, let's just grab everything to the end, and we should be good to go. Okay. And then later on, we'll split the valves on comma and space to figure out what they actually are. There's probably some way to do that with regular expressions. Please let me know down in the comments. How do you split? Yeah, how can you use a capture group to grab an array of things? I don't know. Maybe it's like a fancy regular expression thing. All right. Now you'll notice that we haven't actually matched all of the results because down here, there is a singular tunnel leads to valve GG. In that case, tunnels is plural, but this S at the end is optional. And if we have an S for leads, we want to make that optional. And finally, we want to make the S on valves optional, which we can do by dropping on the question mark there. So now we're able to match them all, and we have the right sort of rates and stuff. So we'll use this as our regular expression here. And we're going to match on line. I'm going to say .match line. And this is going to give us back our match. And now what we want to do is say, yeah, valves at the match name is equal to the rate. And we want to say our graph at the match name is the valves.split. Wow, that's really nice. Okay, so now we'll just say p valves and p graph, and we should be good to go. All right, so we'll say Ruby day 16, and okay, so this is our flow rates. This is all of our flow rates for our valves, and this is all of our adjacencies for our valves. Now what we want to do is traverse the tree, and at each point, we need to figure out whether or not we want to open the valve, and then we also need to go through all of the neighboring valves and see if there's one of them that's going to return the best flow rate at the end. Here's how we're going to do this. Let's make a method called max flow. Here we'll pass in the value of the current valve that we're looking at. We'll pass in all of the opened valves, and then we'll also pass in like how much time we have left. And the idea is that we're going to recursively call max flow with something, something, something time -1. And then ultimately we will execute this with like max flow of AA with an empty list. And then we have 30 minutes. So we'll pass in 30, and this should give us back, hopefully this should give us back some amount that gives us like the maximum possible flow through through all of the opened valves if we went through in the optimal with the optimal approach. So as we're going through each of the valves, we estimated it's going to take 1 minute to open a single valve and 1 minute to follow any tunnel from one valve to another. Here, what we need to figure out is what is the max of opening the current valve, and then what is the max if we were to open, or if we were to travel to another tunnel. Here we want to say something like, if we open the current valve, we want to say something like, if opened does not include current. Like if we haven't already opened this one, then we can consider opening it. And if we open it, then what we want to do is add the current valve into the list of opened valves. Then what we want to do is, now we need to calculate how much pressure will be released as a result of opening this current valves. Current valves times the amount of time that there is left. This is the time left. Otherwise, we're going to recursively call max flow, passing the time down to the next one. Okay, otherwise, even if we didn't open the current valve, we want to go through all of the neighboring tunnels and figure out if any of those will ultimately lead to a better max flow. We want to go through graph of the current at each. And for each one of these, we want to see, so the max is going to be max flow of the next valve passing down opened and, okay. In both, because we want to open this, we want to consider opening the valve as us spending a step and going to the next way. And then we also want to consider going through all of our adjacencies. We need both of these to happen for the same time. And then we want to take the better of the two, right? Here we want to start with max is equal to 0. And then ultimately we're going to return max at the end of this. Instead of just grabbing max is equal to the max flow and max is equal to the max flow here, what we need to do is grab the maximum of max or max flow. Another way to say this would be something like current max is max flow of current. And then we want to say max is equal to current max if current max is greater than max. We want to do this in both cases. In this case, we're going to say we're passing down the next value. And instead of modifying opened here by shoveling in current, we don't actually want to modify that underlying array. Instead, what we want to do is pass down some new current. Open is going to be opened plus this new current value. And the reason is that when we recurse, we want to only consider this new current opened if we've opened a valve here. If we were to modify that, then we would be passing down the modified opened for each of our adjacent neighbors. Okay, this is going to be really slow because max flow in this case, we're not caching anything, we're just constantly recursively calling, but we will, as we're going through all the tunnels, we're going to visit the same valve multiple times. And what our base case here is going to be return 0 if time is less than or equal to 0. Okay, and now if we run max flow for AA through this tunnel, let's just see what we get. Okay, no next value, but it's right there. What are you talking about? Next, oh, valve, next valve. I said next value. Okay, now we're getting stack level too deep. Okay, for some reason, we are recursively calling too much, right? We're going way too far. Oh, so instead of time plus 1, we actually want to subtract time here. And we're going to start at 30, and we're counting down to 0. So that was going the wrong direction there. Okay, it's hanging, it's hanging. In this case, if you go to run something and it hangs for more than a couple seconds, you want to kill it and then give yourself some output. Here, we'll put like current opened in the current time and just see what this looks like. All right, so this, if we scroll back and look at this, you can tell, all right, it's looking at, what if we had opened AA, then DD, then CC, then BB at time 1? And it would tell us like, okay, this is the max possible value at this point. We'll print max down here. Are we making it here yet? So we're not actually, let's see. No, we're not making it there yet. Okay. One thing that we need to do is if we were to look at all of this output, we would find that there are several, look at this, there's several calls with the opened being AADDCC. If we were to search for this, then we would find that there are a ton of repeating versions of this AADDCC with repeating. So the current was D, the current was D, and we had to open up that sort of several times, or we went through that same flow several times. What I want to do is create a cache, which will store as a dictionary, and we need to create a key for this cache. I think we can pass current, opened, and time as our key. And now we want to return the cache key we want to return the cache at that key if there is a key in it with that value. So here we're going to say cache. If we found a max, let's store that off in the cache at this key, and we'll run it again. Looking at our key, this is still too slow. Looking at our key, current is a string, opened is an array, and time is a number. Now, when we think about this opened array, so if we were to just like print out, let's p key for a second. And if we think about this array, you'll notice that a lot of times we're going to be like visiting the same nodes several times. And then if we were to go through, so here you'll notice that we've already gone through AADDCCJJ, and we've already talked about, let's see. If we look at this opened value here, you'll notice that we have A, D, C. So D and C are not ordered. And so it's possible that we somehow went to C before D. In this case, notice that we are at EE now, but we could have already seen EE. So one way that we can improve our cache key is by sorting opened before we encounter it. Let's run this again. All right, we got 0 back, which seems wrong. So our current max is going to be pressure plus the max flow when we recurse. And then in this case, we're just spending, we're not increasing the current max by anything because we're spending the time to go to that new valve. In this case, we are increasing the current max because we are opening a valve. So let's try this again. All right, we got 1,732. And let's look at our answer here. The puzzle answer was 1,986. Oh, actually, let's see. Yeah, okay, so we're still doing the test approach. So we're looking for 1651. So that was too high. Right here, I forgot that when you open a valve, it does not increase the pressure for the current minute. So we need to do time -1 here. I think this might be the problem. Let's see, we want to do the current, we want to release the current valve at time -1. Okay, there we go. 1,651. That was the answer for part 1. And then that's like the answer for the test input. We can grab our puzzle input here and open up input, drop it in, and then run Ruby day 16 against the input. This is another one of the puzzles where it takes a really long time for the input to run. In fact, for part 2, it took my solution a really, really, really long time to run. We're not actually going to solve part 2 today, but the solution is very similar. There's a couple different small optimizations that you need to make, but hopefully this solving of part 1 gets you far enough and we learned about one more approach to traversing through a graph and also calculating, in this case, so using dynamic programming to build up an optimal path through the graph. All right, this is taking too long. I forgot one other optimization that we can make, so let's kill that, come back over here. Now, if the pressure does not equal 0, if the pressure is 0, we don't actually care about going down this path. And so we don't need to make this recursive call, and we can kill this entire branch if the pressure is 0. Let's add that in and we'll rerun our code. All right, there we go, 1,986. We come back over here, 1,986 was the puzzle answer for part 2, that's the puzzle answer for part 1. Now in part 2, it gets a little bit different. The time goes down to 26 minutes, and now you're gonna have an elephant work with you to open different valves. And so the logic becomes a little bit different, but we're not gonna get into that today. Because part 2 takes so long to run, I'm actually just gonna skip over part 2 and head right into day 17. Thanks so much for watching. Hope you enjoyed it, and we'll see you in the next one.